So in this question, we are told that there are two cars that are 100 kilometers apart and traveling at constant velocities in the opposite directions. So we have one car going to the east, one car going to the west. They're 100 kilometers apart. And we know that the red car, which is the car that's moving to the east, is moving with a velocity of 80 kilometers per hour. We don't know the velocity of the orange car, but the orange car is the one that's moving to the west. Now after 1 hour, the cars will pass each other. So in our diagram, we can draw it here, and the cars will be at the same position because they're passing each other. And this happens after 1 hour. With that, we are asked, what is the orange car's velocity? You might not know where to start with this question, but the best way to start with any question is to write down what was given. Right off the bat, we were told that the velocity of the red car, and I write it VR because we want to differentiate between the velocity of the red and orange car, is 80 kilometers an hour. We also know that delta t, the time that passed while we changed positions, was 1 hour. Now it may not seem obvious, but we were also given the initial positions of both vehicles, which would be XIR for the initial position of the red car and XIO for the initial position of the orange car. If we imagine our diagram is like a number line, the red car is at position 0 kilometers. It's right at the start of the number line. And because the orange car is 100 kilometers away from the red car, it must be at an initial position of 100 kilometers. That means XIR, the initial position of the red car, is 0 kilometers, and XIO, the initial position of the orange car, is 100 kilometers. The next piece of information that we know that might not be obvious is about the final position of the cars. So XFR and XFO. This question says that the cars pass each other. And when the cars pass each other, they are at the same position. So we can say that the final position of the red car is equal to the final position of the orange car. So I will say that XFR and XFO are the same, so they can just be written as XF. No need for the subscripts because the final position is the same for both vehicles. Now I always like to remind myself, what are we even solving for? We are solving for the velocity of the orange car. With that, let's look at the equations we can use to solve this. We were told the cars are moving with a constant velocity. When you see the word constant velocity, you know you're moving with uniform motion, so there's no acceleration. And that should cue in that you can use the velocity equation, which says v is equal to the change in position delta x divided by the time it takes to change the position delta t. And we know we can expand this equation out and write it as v is equal to xf minus xi divided by delta t. And the reason I said that we need equations, plural, is because we have two objects. So we're going to need a velocity equation for the red car and a velocity equation for the orange car. The velocity of the red car would be VR is equal to xf minus xir divided by delta t, whereas the velocity of the orange car would be VO is equal to xf minus xio divided by delta t. Now that we have our two equations, let's think about our game plan for answering this question. We know we are solving for VO, the velocity of the orange car. Let's see what we have that we can use to plug into this equation to solve for VO. We know we have our initial position for the orange car, we have our delta t, but we don't have the final position for the orange car. But now let's look at the velocity of our red car equation. We have VR, we have XIR, and we have delta t, which means we have enough to solve for the final position. If we use our VR equation to solve for the final position, we can plug that in to our VO equation and solve for VO. So that is our game plan. Now on a clean sheet, let's start solving. I always like to start by writing out my equations. So we'll write out the VR equation and we'll write out the VO equation. Then what we want to do is use the VR equation to solve for XF. We'll start by rearranging our equation to isolate xf, the final position. Once I've rearranged my equation, I can just plug in my numbers. We know the velocity of the red car was 80 kilometers an hour, the time that passed while the cars were in motion was 1 hour, and we know the initial position of the red car was 0 kilometers. With that, we can solve for our final position, which is 80 kilometers. And now that we have the final position, we have all the variables we need to solve for VO, the velocity of the orange car. And so at this point, we just need to plug our values in and solve for VO. So we have XF is 80 kilometers, XIO was 100 kilometers, and delta T was 1 hour. So VO is equal to negative 20 kilometers an hour. And that is the answer to our question. You might be wondering why the answer is negative. Well, we know velocity is a vector, which means it has both magnitude and direction. The magnitude is 20 kilometers an hour. The direction is given by the negative sign. This negative sign tells us that the car was moving to the left. It was moving west. What this means is that objects moving to the right have a positive velocity, while objects moving to the left have a negative velocity. And that's why our answer to this question was that the velocity of the orange car is negative 20 kilometers an hour.